Hi all, I am K. Surya, working as Assistant Professor in the Department of ECE at SNS College of Technology. In this video, let us see about gray to binary code converter. The gray code is also known as reflected binary code. So it is an ordering of binary numeral system such that two successive values differ in only one bit. Gray codes are very useful in the normal sequence of binary numbers generated by the hardware that may cause an error or ambiguity during the transition from one number to the next. So the gray code can eliminate this problem easily since only one bit changes its value during any transition between the two numbers. So we will see how to convert a gray code to a binary code. The most significant bit of the binary code is always equal to the MSB of the given gray code. Other bits of the output binary code can be obtained by checking the gray code bit as that index. If the current gray code bit is 0, then copy the previous binary code bit, else copy the invert of the previous binary code. Gray codes are used in rotary and optical encoders, Karnaugh maps, and error detection. The Hamming distance of two neighbors gray codes is always 1, and also first gray code and the last gray codes also have Hamming distance is always 1. So it's also called cyclic codes. We can convert a gray code to a binary number using the following method. Consider you are having the following code 10101. So as you know, the first bit 1, you'll be writing it as such. So the binary code is 1 for the first bit. Then we'll performing XOR operation of this current output with the second bit of the gray code. That is as shown here 1 XOR with 1. So you'll be getting the answer as 0. So again this answer 0 will be XORed with the third bit of the gray code which is 0. So 0 XOR with 0 will be 0. Next 0 XOR with 1 will be 1. 1 XOR with 0 is 1 and 1 XOR with 1 is 0 as shown here in the arrow mark. So each and every bit of the output is XORed with the current bit of the input. The first bit alone you'll be writing it as such. So this is how a gray code is converted into a binary code. So this is the truth table of gray code to binary code conversion. So as we saw already, binary to gray code, this is the same as that. So for each of the binary outputs B1, B2, B3 and B4, we will be drawing the Karnaugh map with inputs as A, B, C, D, and we'll be finding out the expression. So as shown here, so this is the Karnaugh map for B4 and B3. So for B4, you'll be getting 8 ones which is grouped together, and the common variable for the all these 8 ones is A. So B4 is equal to A. Next one, B3 is equal to, as shown here, A bar B plus A B bar. So which is nothing but A XOR with B. So next one is B2. As shown here, we can group only two ones. So B2 is equal to A bar B C bar plus A B bar C bar plus A bar B bar C plus A B C. So when we group this, we will be taking A as common in the second term and the fourth term. So you'll be getting B bar C bar plus BC, and we'll be taking A bar as common in the first term and the third term. So we'll be getting BC bar plus B bar C. So we know that B bar C bar plus BC is nothing but XNOR gate, and B C bar plus B bar C is XOR gate. So we can tell that A into B XOR with C the whole bar plus A bar into B XOR with C. So we'll be getting A XOR with B XOR with C as the answer. Similarly, for B1, since we cannot group anything, we'll be writing the terms for each and every one individually. And then if we simplify that, we'll be getting A XOR with B XOR with C XOR with D. So this is the logic diagram. So you'll be getting B4 is equal to A, B3 is nothing but A XOR with B, B2 is A XOR with B XOR with C, and B1 is A XOR with B XOR with C XOR with D, as shown here. So here, when we give a gray code A, B, C, D as input, we'll be getting the corresponding binary code B4, B3, B2, and B1. So this is the design of gray to binary code converter. Let us see few applications of gray to binary code converter. So the gray code is used in a few specific applications. The main applications include being used in analog to digital converters as well as being used for error correction in digital communication. Gray code is used to minimize errors in converting analog signals to digital signals. Some other applications of gray code are Boolean circuit minimization, communication between the clock domains, error correction, genetic algorithms, mathematical puzzles, and position encoders. Some of the advantages of gray codes are it is better for error minimization in converting analog signals to digital signals. It reduces the occurrence of Hamming walls and undesirable state when used in genetic algorithms, and it can be used to in the minimize the logic circuit, and it is also useful in clock domain crossing. One main disadvantage of the gray code is that it's not suitable for arithmetic operations, and its limited practical use outside of a few specific applications. Hope you understood gray to binary code converters. Now let us take up some assessment questions. Why do we use a gray code? The options are to count the number of bits changes, to rotate a shaft, error correction, and error reduction. Yes, the gray code is used in error correction. Reflected binary code is also known as dash. The options are BCD code, binary code, ASCII code, and gray code. Yes, the answer is reflected binary code. It's also known as gray code. Thank you for watching this video.